Speech recognition has come a long way in the last couple of decades. The systems are getting very good, and you might be wondering why. It's not just simple pattern matching. If you look closely, a speech recognition system will transcribe your words, but sometimes it will back up and make a correction as you speak. For instance, I just spoke into my phone this sentence: I put the flower in the garden. And as I said these words in order, the transcription kept changing. It went from I to iPad, to I put the flower, to I put the flower and the guy, to I put the flower in the garden. It can be fun and almost comical to watch this. What's going on? In previous lectures, we've seen how important it is to understand matrix powers. For instance, in the dynamics of foxes and rabbits, we saw the population vector at time n+1 was a linear transformation applied to the time n population vector. The populations evolved by repeated application of a matrix. Now we're going to see another common scenario in which repeated application of a matrix is involved. In this case, the coefficients of the linear equations come from probabilities. And the matrix will act on the right rather than the left. We'll consider a very simple model for the weather. Let's imagine that there are just two possible states on any given day: rain and sun. Of course, the weather changes over the day, but for simplicity, let's just define a rainy day to be one in which it rains anytime during the day, and call a day sunny if it doesn't rain anytime during that day. We'll think of the weather as a process which evolves from day to day, transitioning between states or staying in the same state with certain probabilities. We're going to assume that the weather tomorrow only depends on the weather today and not on any days before. Suppose that if it is sunny today, there's a 90% chance that it stays sunny, but a 10% chance that it will rain tomorrow. And if it is rainy today, there's a 70% chance it will clear up tomorrow, but a 30% chance that it will stay rainy. So our diagram here shows the probabilities of transitioning between the states. Let's write down algebraically what's going on. Put these transition probabilities in a matrix called the transition matrix, like so. We'll put today's states in the rows and tomorrow's states in the columns, and the entry in row I and column J represent the probability of transitioning from state I to state J. So, for example, the top left entry in the transition matrix, 0.9, is the 90% probability of starting in a sunny state today and remaining in a sunny state tomorrow. Transitioning from state I to itself just means staying in the same state. The top right entry says there's a 10% chance of going from sun today to rain tomorrow. Notice that the row entries must sum to 1 because the total probability of transitioning out of any state should sum to 1. Now, if we have the likelihood of being in these states right now, then we can figure out what the likelihood of being in the states is the next day. So let's give these quantities a name. Let's let x sub I of n be the probability of being in state I at time n. So we'll condition on the weather today, day n, to get to the weather tomorrow, day n+1. So if I want the probability of a sunny day on day n+1, I can find that as the probability of a rainy day on day n times a probability of going from rain to sun, which is 0.7 or 70%, plus the probability of a sunny day on day n times the probability of going from sun to sun, which is 0.9. Similarly, if I want the probability of a rainy day on day n+1, I can find that as the probability of a rainy day on day n times the probability of going from rain to rain, 0.3, plus the probability of a sunny day on day n times the probability of going from sun to rain, 0.1. Do you see now that we have a system of linear equations? If we let the vector x of n be the row vector whose components are the likelihoods of sun and rain on day n, and let A denote the transition matrix, then the vector x of n plus 1 is just x of n times the transition matrix A. Notice how, unlike the fox-rabbit situation, we are multiplying the matrix A on the right, not the left. Then, if the vector x of 0 is the initial likelihoods of sun and rain, we see that x of n is just x of 0 times a to the n, since we are just repeating the action of the transition matrix n times. From this equation, we can see that the ijth entry of a to the n actually has an important meaning. Let's let p sub ij, superscript parentheses n, denote this ijth entry of a to the n. I claim it is the probability to get from state I to state j in exactly n days. To see why, we can use the row-column formula for matrix multiplication. From that, we see that the ijth entry of a squared is just the sum of pik times pkj summed over all k. And this quantity, p sub ik times p sub kj, is the probability of going from I to k and k to j. So the sum includes all the possible intermediate states for a two-step path from I to j. And if you argue inductively, you'll see that the ijth entry of a cubed is the sum of the products of probabilities of going from I to k to L to j, summed over all intermediate states k and L. And the same general pattern holds for all n. So you see, once again, matrix powers become important to understand. So if A is this transition matrix, then let's look at some of the powers of A to see what we observe. A squared gives all the two-step probabilities and looks like this. Now look at a to the fourth. We see all the four-step probabilities. You begin to see the rows look similar. Now look at a to the 10th. The rows are all basically identical now. What does this mean? Since each row contains probabilities that all originated from a particular state, the fact that the rows are identical means the long-term likelihood of being in sun or rain in 10 days doesn't matter which starting state you start in. No matter where you start in the long term, 7/8 of the time it will be sunny, and 1/8 of the time it will be rainy. Why did this happen? Was it an unusual occurrence? This example we just explored is an example of what we call a Markov chain. A Markov chain is a process with a finite number of states. It moves from state to state, and at each step, the next state only depends on the current state, and importantly, not on past states. The state of the process evolves according to some probabilities of transition. If we let p sub ij be the probability of going from state I to state j at any step of the process, then we can form the transition matrix A, whose entries are the transition probabilities p sub ij. Note that a consequence of the definition is that each row of the transition matrix must sum to 1, because each row contains all the probabilities of transitioning out of some particular state in the system. Let x sub I of n be the probability of being in state I at time n. Then let vector x of n be a row vector that collects these probabilities together for time n. Then, as before, the vector x at time n equals the vector x at time 0 times the matrix a to the n. Note again that the vector of probabilities evolves linearly according to multiplication by a matrix on the right. Let's look at another example to see what we can find. Suppose we wish to model economic mobility. And for the sake of simplicity, let's suppose there are three classes of people as measured by wealth: rich, middle class, and poor. The people in each category may move around, so we might look at the probabilities of shifting from one class to another and ask, what's going to happen to the distribution of people in the long run? If I know their current wealth, we'll assume that their future wealth depends only on how much money they have now, not on their status at any other moment in the past. So this can be modeled by a Markov chain. Let's measure time in decades and suppose the transition probabilities are given by this hypothetical transition matrix. As before, the rows represent the current state and the columns the state being transitioned to. Looking at the first row, what these probabilities suggest is if you're rich, the probability of staying rich in the next decade is quite high. The probability of going poor is 0. The second row is the row where you start out middle class. Becoming rich is very unlikely, 2%, but the probability of staying in the middle class is very high, and there's a 20% chance of becoming poor. The third row shows if you're poor, the probability of staying poor is high, and there's a negligible chance of becoming rich in the next decade. Let's investigate what happens in the long term. As before, if the transition matrix is A, then the matrix power a to the n gives the n-step probabilities of going from one state to another. In particular, the ijth entry is the probability of going from state I to state j in exactly n steps. And now a to the 5th looks like this, a to the 10th looks like this, and a to the 100 looks like this. After 100 steps, it's clear that the rows are converging to the same distribution. In other words, no matter what distribution of rich, middle class, poor looks like when you start, the distribution of people in this country is going to look the same in the long run. 44% rich, 27% middle class, 29% poor. So something very interesting is happening. Let's see if we can figure out what. In both of the examples we discussed, we see that the Markov chains appear to be converging to a limited distribution called the steady state vector. Why is that? The property of a steady state vector is that when the transition matrix is applied, it remains the same. So if W is a steady state vector, then W equals W times A. Now, where have we seen an equation like that? Notice that this looks a lot like the eigenvector property, except that the vector is on the left of the matrix A and it is a row vector. In fact, this is what's called a left eigenvector of A. This definition of a left eigenvector is this. We call a row vector W a left eigenvector of A if W times A equals lambda W. Remember that the definition of a usual eigenvector is AV equals lambda V, whereas this is WA equals lambda W. The usual eigenvector is sometimes called a right eigenvector, but whenever you hear the word eigenvector without reference to left or right, then it refers to the usual right eigenvector. In a similar fashion, we can define a left eigenspace and left eigenvalue. But we don't need to develop a separate theory of left eigenstuff because there's a simple connection to right eigenstuff through the transpose. Look at the left eigenvector equation and take the transpose of both sides. What we get now is A transpose times the column vector W transpose on the right equals lambda times W transpose. In other words, W transpose is a right eigenvector of A transpose. So we've just established the following theorem. W is a left eigenvector and lambda is a left eigenvalue of A if and only if W transpose is a right eigenvector and lambda is a right eigenvalue of A transpose. Now to our study of Markov chains. We first want to know, does every Markov chain have a steady state vector? Indeed, the answer is yes. To show that, let's establish this theorem, that A and A transpose have the same eigenvalues. To prove this, note that since an eigenvalue is a root of the characteristic polynomial, it's enough to show that the characteristic polynomial of A and A transpose are the same. But the characteristic polynomial of A is determinant of A minus lambda I. And the characteristic polynomial of A transpose is the determinant of A transpose minus lambda I. So we'll now show that those two things are the same by appealing to two facts easily verified. The first is that the transpose of the identity is just the identity, and the second is the transpose of a sum is the sum of the transposes. Then, the quantity A minus lambda I transpose is just A transpose minus lambda times I transpose, which equals A transpose minus lambda I. But since the determinant of a matrix and its transpose are the same, we have that determinant of A minus lambda I equals the determinant of the quantity A minus lambda I transpose, which equals the determinant of A transpose minus lambda I. So we see that the characteristic polynomials of A and A transpose must be the same as well. So then A and A transpose have the same eigenvalues as we'd hoped to show. And that's the end of our proof. So then, what are the eigenvalues of A? Well, it's easy to see that A has eigenvalue 1 because the rows of A must all sum to 1 since they form a complete set of probabilities of transitioning out of some particular state. So you can multiply A by the vector of all 1s to sum the rows. But this means that A times the vector of all 1s must be the vector of all 1s. So 1 is an eigenvalue of A. So then A transpose must have eigenvalue 1 as well. So there must be an eigenvector V such that A transpose V equals V. And you can scale V so that its entries sum to 1 and it'll still be an eigenvector. So notice that the row vector V transpose now satisfies V transpose A equals V transpose. This means that W equals V transpose is the steady state vector that we were looking for. Could there be more than one steady state vector? That's the next question. The answer to that is yes. Some Markov chains have multiple steady state vectors. For instance, if a Markov chain has a transition matrix that's the identity matrix, then every vector is a steady state vector because clearly W equals Wi for any row vector W. With the identity as transition matrix, it's just saying that the Markov chain stays put for all time. If you start in a state, you're stuck, you never move. So clearly there are multiple steady states. Okay, so what if we require our process to move around more? Would there necessarily be a unique steady state vector then? The answer is, under reasonable conditions, yes. Let's call a matrix positive if all its entries are positive. And let's call a Markov chain regular if some power of the transition matrix is positive. What this means is, after some number of steps, it's possible to transition from any state to any other state with positive probability. That should keep us from getting stuck in one part of the chain. Then, there's an important theorem called the Perron-Frobenius theorem that shows that the steady state vector is unique and every starting configuration will converge to it. So here's what Perron-Frobenius theorem says. If A is a transition matrix of a regular Markov chain, then 1 is an eigenvalue. The left eigenspace of A associated to the eigenvalue 1 is one-dimensional. There's a left eigenvector in that eigenspace with all positive coordinates. And if lambda is any other eigenvalue, then the absolute value of lambda is strictly less than 1, even for complex eigenvalues. Okay, so what can we say about this theorem? Well, we've already shown the first statement, that 1 is an eigenvalue of A. We won't prove the other statements here, but let's talk about their consequences. If talk of left eigenvectors and left eigenspaces makes you uncomfortable, remember the matrix A acts on left eigenspaces by multiplying on the right, just as the matrix A transpose acts on its right eigenspaces by multiplication on the left. So, as you'd expect, if the action of A on a left eigenspace scales everything in that eigenspace by a factor, just as it does for right eigenspaces, the left eigenspace associated to 1 stays fixed under action by A. Because that eigenspace is a one-dimensional line, every eigenvector in that eigenspace is a multiple of 1 with all positive coordinates. Then we see there is exactly one of those multiples whose coordinates sum to 1. That must be the steady-state vector of A. So this shows that it's unique. There is no other steady-state vector. The fact that all other eigenvalues are strictly less than 1, even complex eigenvalues, suggests that any initial row vector well through multiplication by A repeatedly converge to the same steady-state eigenvector. This is most obvious now in the case where A is diagonalizable, because there's a basis of eigenvectors and they're all contracting except the steady-state vector. So any starting vector must contract towards the eigenspace for 1. But the theorem is true even if A is not diagonalizable. That's where the hard work is in proving the theorem. This explains why as n goes to infinity, A to the n will converge to a matrix whose rows are identical and equal to a steady-state vector W. Because the ith row of A to the n is just what you get when you multiply the standard row basis vector EI transpose by A to the n. If any starting vector converges to the steady state, then we expect each row of A to the n converge to the steady state vector as well. So let's return again to the model that we discussed in the past about surfing the web, where we had an adjacency matrix M and saw that powers of M counted the number of paths between nodes in the graph after M steps. We had suggested a crude way to rank a web page by counting the average number of paths to that page after a large number of steps, then using that score to compare the relative scores across web pages. And we have no guarantees that this kind of scoring would behave well as a ranking algorithm. But we can modify it to behave like a Markov chain, and then the Perron-Frobenius theorem can help us. This was the idea behind Google's PageRank algorithm. The underlying model is a Markov chain model of the web. We'll imagine a web where each page is a state in the chain, and there's a random surfer who, at each time step, picks a web page at random with uniform probability and moves to that page if there's a link from the current page to that page. That's the Markov chain. Let's look at the small 4-page web from our earlier example. The nodes are A, B, C, and D. Let's record the probabilities of moving between nodes in the transition matrix that we'll call capital P. And it looks like this. Notice that because B has 3 links going out, that the transition probabilities are 1/3 for each of the links out of that page. But C has only 2 links going out, so the transition probabilities will be 1/2 for each link going out. Okay, so this is a Markov chain. It's not clear that it's going to be regular, but if you study the web a little bit, you'll see that every node can reach every other node in exactly 4 steps. So the Perron-Frobenius theorem says that p to the n will converge with all rows going to the steady state vector. Before we compute it, can you guess what that vector will be? For instance, which node is a surfer most likely to be in after a large number of steps? Which one will be the most highly ranked, do you think? You can probably guess that A and D will probably have the same page rank, since they serve symmetric functions in the web. But will B have the same rank, or larger, or smaller than A and D? And what about C? So when you calculate p to the 100, you get this. And now you see each row has converged to the steady state vector. Of course, you didn't need to take p to the 100 to find the steady state vector, because you now know that you could have just looked at the dominant eigenvector of p transpose, the one associated with the eigenvalue 1. This is, by the way, the same as the dominant left eigenvector of p. And if you did that, you'd find the steady state vector to be 3/13, 3/13, 4/13, 3/13. Did that surprise you? Or did that make sense intuitively? Now, for an actual web, this kind of page rank is not going to work because the transition matrix P may not be a regular Markov chain. There are a couple of potential problems. The first is how to deal with dangling web pages that have no links out of them. That's a problem because P will have a row of all zeros. We can solve that problem by filling any row of zeros with entries, all 1 over m, where m is the number of web pages in the web. That's like telling the random surfer, if they encounter a dangling page with no links out of it, to just pick a page at random on the entire web for the next state. We'll call this new transition matrix P prime. The second problem is how to deal with the fact that the matrix might still not be regular. The way Google handled this problem was to introduce a damping factor, D, which assumes that the random surfer, no matter what page they are currently in, will, with probability D, just choose a page at random anywhere on the web and hop there. And with probability 1 minus D, will just continue to operate according to P prime. So this new transition matrix is 1 minus D times P prime plus D times the matrix of all entries 1 over m. Now, Google sets the damping factor at 0.15. So what that means is there's a 15% chance of hopping to some random web page anywhere on the web in this particular Markov chain. We'll call this matrix the Google matrix G. Notice that G is actually a positive matrix, so the Perron-Frobenius theorem applies. There will be a steady state vector to which all starting configurations will converge, which is the PageRank vector. If you calculate it for our example, the PageRank vector for our simple web is this. Notice that pages A and D are the same. They have the same page rank at about 0.232. But page B now has actually a little higher page rank at 0.235. Page C is still the most important web page with a PageRank score of 0.301. Now, for doing the actual World Wide Web, this kind of calculation is not as easy because it's a very, very large web. So some sophisticated knowledge of linear algebra and numerical algorithms are used to build on this idea and make something like this workable for a huge web. Now, Markov chains have so many cool applications, and we've just scratched the surface. For instance, in genetics, you often see the incidence of various kinds of dominant or recessive traits remain stable in the population. That's often because there's an underlying regular Markov chain that moves from genotype to genotype, and it's stable because there's convergence to a steady state vector. Then there are some fun things you can try once you know about Markov chains. For instance, think about the sequence of letters you encounter as you read. That's a Markov chain on maybe 40 characters if you allow numbers, spaces, and punctuation. And Andrei Markov himself first discussed these kinds of chains in this context by looking at a poem of Pushkin and measuring the transition probabilities of Cyrillic letters. So here's a fun project. Take a text from any author you like and train your Markov chain on that data by empirically measuring the transition probabilities that a certain letter will be followed by another letter. Then if you run the Markov chain using these probabilities, that's a 40 by 40 transition matrix, you'll end up with some fun sentences that look like English, but they're nonsensical. You could, if you want, do something very similar with music to create random music out of phrases that are states of a Markov chain. And today's speech recognition algorithms build on this idea by viewing speech as generated by what are called hidden Markov models. A rough description goes something like this. My speech generates a sequence of sounds, like consonants and vowels, according to a Markov chain. And that Markov chain might change as I move from word to word because each word has different transition probabilities for the sounds. Meanwhile, the speech software is listening to what I'm saying. It can't see the Markov chains that I'm using. That's what's hidden. But it does see the sounds that I produce. And based on the sounds it's heard so far, it's trying to figure out what the most likely model is that produced that sequence of sounds. So it's adjusting on the fly as we go. That's why your software will sometimes back up when transcribing speech. When I say garden, the likelihood just went down that the word flower I said a few words ago was F-L-O-U-R. It now knows it's F-L-O-W-E-R. So my speech software corrects itself.